Now I'm streaming to the internet. Just started streaming to the internet. Test 1 2. Test 1 2. Test 1 2. Test 1 2. Testing the audio. Test 1 2. Test 1 2. Test 1 2. Test 1 2. Hey, hey, can you tell us whether you're getting audio? Because we are transmitting audio. Hello, testing 1 2 3. Hello, testing 1 2 3. 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 Testing 1 2 3.
background. At each meetup, people from the community will have the opportunity to present their projects and ideas to the group. The event here is being sponsored by Bastille Networks and is being hosted by Qualcomm. Our speaker will be the Phil Karn, who will give a talk titled... Oh, we have. Oh, nobody told me. Okay, no specific order. So one of our speakers will be the Phil Karn, who will give a talk titled Low-Cost General Coverage Ham Receiver for Raspberry Pi and FunCube Dongle or Other Cheap SDR. Another speaker will be Clayton Smith, who will talk about his recent work on HD radio. His past works include digital voice, digital television, utility metering, radio data, and SDR samples. Another speaker will be Josh Bloom, who will talk about interesting features in the Pothos framework, how it pulls in the GNU Radio project, and proposed additions to the GNU Radio. Another speaker will be Alexander Chemra, who will give the first public demonstration of the XTRX radio, which is a tiny, high-performance mini PCI Express SDR real world, and supports up to 120 megasamples per second for simultaneous 2x2 MIMO receive and transmit. Another speaker will be Nate Temple, who will talk about getting... Both? Another speaker will be Temple, who will talk about getting onto the X-band. Recall that Nate spoke at the previous meetup at DEF CON 25 about satellite communications. All meetup presentations will be recorded and posted online, as well as streamed live on YouTube. The videos for the previous Cyberspectrum events have already been posted. We have set up a channel on IRC on Freenode called #Cyberspectrum as a way for people remotely watching the live stream to contact the local group here with any comments or questions, as well as to alert us to any audio-visual problems, although we never have any. Further details will be posted on the meetup page in about 2 weeks prior to the next event, so please tune in, pun intended, for all the details, including a list of speakers and presentation topics. Future meetup locations will return to the Bay Area and will alternate every month between Noisebridge in San Francisco and the Edis Research Office in Santa Clara. We are actively looking for speakers, so if you would like to present something, or if you have ideas about future topics, then please get in touch with us. We would like to thank all of our speakers tonight for their efforts and enthusiasm, and we would also like to thank Bastille Networks for providing complimentary pizza and drinks. We would especially like to thank Qualcomm for providing this meetup space, and thank Mike Osman, Michelle Thompson, and Ken Easton for their quick response and heroic efforts in organizing this event. The event here tonight would not have been possible without them. And with that, we'll now get started. Thank you.
Thanks, Neil. So let's start with our very first presenter, Clayton Smith, who's going to talk about his amazing experiments with HD radio.
Okay. Yeah, that would work. Oops. Oh, I guess can I use the podium? Oops. Yeah, I'm going to mirror my displays here. working? All right, let me just make sure my equipment is up and running. All right, there we go. Thanks for coming out, everybody. Today I wanted to talk about a couple of projects that I've been spending my spare time on for the last little while. And they involve HD radio. So let's jump right in here. When it comes to digital broadcast radio, there's actually a few standards that are in fairly wide use. So today we're going to be talking about HD radio, and there's two others. One is DRM, and the other is DAB and DAB+. And so DRM and DAB+ already have some nice open source implementations. And in fact, Luca right there spent his summer working on a DAB and DAB+ transmitter and receiver. DRM, there's a piece of software called Dream that works pretty well. But and DRM. And then for HD radio, until about a year ago, nothing really existed. And so I was interested in doing something about that situation. If you've ever browsed around the FM broadcast spectrum, you've probably seen a lot of signals like this popping up. You can see in the center there we have an ordinary FM broadcaster, and they've added an HD radio signal, and you can see the digital sidebands above and below. Those are OFDM modulated, and then over to the left and right there's two neighboring broadcasters that haven't turned on an HD radio signal yet. So I started seeing more and more of these things popping up, and I had to look around. I didn't see any GNU radio or any kind of software implementation of HD radio. So about the time of last year's GRCon, I thought, okay, how about I take a crack at making a receiver or a transmitter for this thing. So I started by downloading the standard from the National Radio Systems Committee, which is the standards body that put the HD radio standard together, and dived into that. There's actually quite a lot of details about how the whole thing works, except if you look at the parts that are specified, everything is there except for the one thing that you really need for a radio broadcasting standard, which is the audio codec. And that made me sad. So anyway, I didn't want to let that get in my way. So I did, at last GRCon, start putting together a basic receiver and transmitter. And I thought, okay, that codec business, I'll just leave that for later. And hopefully a solution will come about somehow. So I kind of worked on that through like September, October, November. I put together a really basic receiver that was good enough to pull data off of local stations and extract the metadata they were sending, the station name and what track was playing and all that kind of stuff. I was able to pull out audio packets and log them, of course not decode them. And then I started working on a transmitter and put together enough of that so that I could encode all the metadata. Proper GNU radio module or anything. So I just kind of let it sit and hope that somebody would show up and figure out how that pesky codec works. And I didn't have high hopes for it happening, but you never know. Then suddenly, this past June, this little software security company out of Texas called Theory published this blog post, and they had not only built their own open source receiver for HD radio, they had also cracked the codec. So the project was headed by a guy called Andrew Weezy, and I asked him when I met him at DEF CON, how did you crack that codec? And he told me he had a friend who had extracted a firmware from the radio in a Toyota Prius. And then Andrew, he's really good at reverse engineering. So he just took a crack at the code and eventually found the place where the codec was and worked out how the thing worked. Prior to that, the speculation on the internet was that it's probably some modified version of the high efficiency AAC codec. And that's actually the same codec that's used in both DRM and DAB+. And they each kind of use their own slightly modified version. So it's probably a good assumption that maybe HD radio is doing something similar. And it turned out that's exactly what it was. And actually, it's so similar, you can just take an existing HEAAC implementation and make about 50 lines worth of code changes, and you have a perfectly functioning HD radio decoder or encoder. So Andrew went to the work of making a decoder and got a more or less working HD receiver and published it up to GitHub. It's GPL licensed. This software, currently you can only use it with an RTL SDR because it's just a standalone application that links to librtl SDR. So you can't quite do this in GNU Radio yet. I'm working on doing something about that. But let me just give you a quick demo of how this application works. So it's right now a command line application. There's no GUI or anything. You just run it. You can tell it what gain you want. So I'll tell it to 12 dB of gain. I want to listen to the station at 96.5, and then the 0 at the end means that you want to listen to program number 0. So these stations can have up to 8 sub-channels, and so that just specifies which sub-channel I want to listen to. So I will fire that up, and it takes a little while to lock on, and away we go. So here we're listening to KYXY FM, their first sub-channel. It just kind of prints out a bunch of debug information about what track is currently playing and any other... Oh, you want more volume? Yeah, sure, I'll take... Yeah, and the other interesting thing about this program is it also has a mode where it will dump out any data files.
Round of applause.
There we go. So that's the first sub-channel. If you want to hear the next one, you just punch a 1 in the end and run it again, and now we'll listen to another one of their sub-channels. I think this station has 3 sub-channels. So there we go. There's the second sub-channel and track name and all that kind of stuff. And then some of this other stuff here that's showing up is actually metadata and files that the station is sending out. So these stations can broadcast album art, they can send out weather maps, traffic maps, radar, and all that kind of thing. And this program, if you fire it up with the right command line option, it can even dump all those files out, so you can look at what files are being sent out by the station. So anyway, this project is called NRSC5. It's available in Theory's GitHub repo. It's mostly the work of Andrew Weezy, but I've been contributing a lot of bug fixes and adding new features. So we're kind of collaborating on this. So let's go back. So that's sort of the command line tool. There's a really interesting blog post by Mike Connolly, who figured out that you could take that command line tool and just pipe the audio into some other command line tools that will broadcast the audio throughout your house using Google Cast or AirPlay. So that's kind of a neat way that he found to make use of that software. So that's the NRSC5 receiver. So anyway, once that codec was reverse engineered and we had a working receiver, I thought, you know what, I had built that hacky Python scripts that could transmit HD radio at the end of last year. Why not turn that into a proper GNU radio module and make an encoder so that we can have a full GNU radio-based HD radio transmitter? So I started working on that maybe about 1 month ago. Basically, I just took all those Python scripts that I had written and turned each one into a GNU radio block in an out-of-tree module. And here's what the finished product looks like. You can see that the out-of-tree module, it just adds these 5 NRSC5 blocks down in the corner. There's an HDC encoder, which is the audio codec. And then there's 4 other blocks that are just kind of all about assembling the bits into the right format to generate the OFDM symbols that you then transmit. So all these HDC, or all the HD radio specific blocks are up here at the top. That generates a bunch of symbols, and then you just run those through an inverse FFT because it's a OFDM signal. And then all these blocks that I have down on the bottom are just generating an analog FM signal because these stations, they're a hybrid signal. So they have the analog FM in the middle and the digital signal on the outside. The only reason I did that is because some receivers if you're tuning around, they won't stop on your frequency unless there's something present there in the middle. So I'm just basically modulating a 1000 hertz tone so that it has a signal to lock onto. So that's the flow graph, and I'll show you a demo of that just a little bit later. And yeah, so once I had that built, I came down here to the GNU Radio conference, and I heard from Michelle that she was looking for people to contribute extra problems to the Capture the Flag contest that she was organizing. And I thought about it for a while, and I'm like, I just built this HD radio transmitter, and there's an HD receiver out there that you can use. It's open source. Why not turn that into a Capture the Flag problem? I'll make an HD radio signal, hide a few flags in there, and give some clues for how to find them. And I got thinking about it a little bit more, like how can I make it obvious that this is an HD radio signal, and like suggest maybe what kind of tool you could use to receive the thing. And it occurred to me that because it's an OFDM signal, and in HD radio, the OFDM subcarriers are either BPSK in the case of the pilot subcarriers, or QPSK in the case of the data carriers. Both of them are PSK, and all the information is contained in the phase of the signal. The amplitude does not matter at all. And GR paint, it does the same thing, right? If you want to paint something onto the spectrum, you just vary the amplitude of a bunch of OFDM carriers, and now you're painting a picture in the waterfall. So I decided to do the same thing for HD radio and paint a clue into the HD radio signal. So behold the HD radio Doge. So if you're at a GRCon and haven't looked for this thing yet, browse around in GQRX or whatever your favorite SDR receiver is, and you will find it there. And that gets you started into some of the other problems that come after. So once you find that, fire up the NRSC5 receiver and see what pops out. You might get some points for it. And actually, it turned out it was not even that much code to make that happen. So this is basically the entire script that I used to paint the Doge onto the HD radio signal. This little Python script, all it does is it reads in a image, it scales it down to the right size corresponding to the number of OFDM subcarriers. There's 191 in each of the sidebands, so I just scale it down to 191 pixels wide. Then I convert it to black and white, rotate it 180 degrees because the waterfall goes from top to bottom, so you need to paint the image from bottom to top. And then I just take the intensity of each pixel and convert it to an amplitude scaling factor and write it out to a file. And then you just have to make a little 2-block modification to the flow graph. I just added a file source there to pull in those amplitude factors, and then a multiply block to multiply the amplitude into the OFDM symbols, and away you go. So there's, of course, still some other work left to be done in these projects. Most of the, all the important parts of the HD radio standard for FM are already implemented, but there's still lots of bells and whistles and things that haven't yet been implemented. One big missing thing still is an AM receiver and transmitter. So the HD radio standard, there's also a version of it for AM. Obviously the bandwidth is much narrower, so the FM signals are about 400 kilohertz wide. AM, it's only 30 kilohertz wide, so they really need to reduce the bit rate and pack things in very tightly for it to work on AM. And all the parts that are needed are there. It uses the same codec. Most of the implementation is the same. It's just kind of like the physical layer that's different. And so, you know, it should be not too big of a job to make an AM receiver and transmitter work. I had a look, and there seems to be a local transmitter here on 950 kilohertz. Oh, is it? Okay. The only one I know of. Yeah. And somebody sent me a sample of the one in like the Dallas-Fort Worth area. I listened when I was in Vegas too, and I heard.
Sounds like that's absolutely ripe for fuzzing.
We good? Okay. Yeah, the only thing that makes fuzzing difficult is just that you get about 100 kilobits worth of bandwidth, so you can't, you know, blast out that many test cases in a short time, and you know you'll have a hard time knowing when a crash has occurred because it's a different device that you're fuzzing over a radio link. But anyway, I'm sure there are bugs out there that would let you exploit HD radio receivers. So yeah, that's about all I got. If you're interested in participating, I would love to have collaborators on this project, you know, helping me out with testing or adding features, writing code, whatever. So have fun.
Questions from the audience? Anyone with questions?
So, okay. So with reverse engineering the codec for HD radio, is there any worry about like a DMCA violation?
If anything, it would be a patent issue. So there are patents that cover the HEAAC codec, and so presumably they would cover also this slightly modified version. So if you distribute binaries of the code, or if you compile it and run it on your own machine, you could be running afoul of patent laws. But you know, I'm just distributing the source code, so you know what you do with it is up to you.
Thank you.
What was the most surprising feature or part of the NRSC 5 standard that you found while implementing this?
I mean, I think like a lot of standards, there's like a lot of things that are in the standard but aren't actually used in practice. Like for example, there are many, I think there's about 12 different modes that you can configure the thing in that like change the bit rates of different sub-channels and things. And in practice, every single broadcaster that I've received, which is about like 40 so far, is using either mode 1 or mode 3. So I'm not sure why that is, but I guess there's not really much interest in the other modes.
Any other questions?
mentioned building a transmitter. Is there any FCC regulation to use your open source transmitter?
I guess like anything, if you're transmitting, you need to know your local laws and whether you're allowed to transmit on the frequencies that you're transmitting on. A lot of the experiments that I've been doing, I'm a licensed amateur, and so I'm transmitting in amateur bands and putting my call sign in the transmission and everything to make sure I stay legal. Yeah.
Like on the license issue, so at least in Europe and in the US, it's like audio purpose small range FM transmitter are legal with very low output buffer. So basically for in-car operation, that's usually fine.
Yeah, I think you're allowed 1 microwatt.
So that depends. Like I think the American thing is actually like even stricter than the European one, but that was like 50 nanowatts or something. So really, really, really little.
Hi there. What's the highest and lowest like AAC bit rate that's actually inside this thing? How many channels can you pack, or what's the highest quality signal you can actually pump out?
The codec goes from 8 kilobits per second up to 96 kilobits per second, and I mean it's quite an efficient codec. So I think by the time you get up to 96, it's like indistinguishable from the original source audio for a stereo signal. And like as far as how many stations you can, or how many like substations you could pack in, it depends which mode you're operating in. So in the mode 1, which is the most basic mode and it's most commonly used, the total bit rate is about 100 kilobits per second. So you can divide that up. You can divide that up however you like among the subchannels. They do also have a digital only mode. So when you're ready to shut down your analog station, you can fill in all the space in between with digital subcarriers. And then you can get up to, I think, about 250 kilobits per second. So that would be enough to maybe have 5 or 6 audio channels. In practice, all the stations that I've found have either had 1, 2, or 3 subchannels, but you can go up to 8.
Question from the internet. Did you try to fuzz commercial receivers with the HD radio signal?
I have not tried any fuzzing yet, no.
Is there anyone transmitting on the DAB and the other standard, the DRM standards?
Not in North America that I know of. In Canada, there was a period about 10 years ago where broadcasters started experimenting with DAB, but they shut down all the transmitters. So as far as I know, all the DAB is in like Europe and other parts of the world. And DRM, it's shortwave broadcasters, and mostly in Europe and Asia.
So these are really like dead standards that never really took off then.
I mean, there's a decent number of DRM, and there's a lot of DAB broadcasters, especially in Europe. And like in Norway, they're shutting off analog FM, and it's all going to be completely replaced by DAB.
Another question from IRC. Is there any relationship between the channel number and whether it's on the left or right subcarrier?
Actually, the left and right subcarriers kind of are both part of the same signal. So there's a interleaver which kind of scrambles the bits throughout the entire signal. And so, like in the basic mode, there's 191 digital subcarriers on either side, and the signal is equally distributed between the two. If you get into some of the other modes, like mode 3, they start adding extra bands of subcarriers closer to the FM, the analog FM, and those are actually separate. So in most of the broadcasters that I've seen so far, they'll have their HD1 and HD2 subchannels in the main outer sidebands, and then they have ones that are closer in that have the third subchannel. But if you look at the standard, there's like all sorts of ways of mixing and matching that.
In the flow graph that you're currently showing, why do you have 2 rational resamplers right after each other?
I think I put that there just to make sure. I thought it was more efficient if you have a couple cascaded that each have small numerators and denominators. I didn't actually test whether that was the case, but and actually, while I have this up, I may as well fire it up and just show you that my Doge signal actually works on a real receiver. I have a receiver over here, so we'll fire it up here. So right now you're just hearing silence because I'm not transmitting anything. And now I'll fire up the Doge transmitter. If you have SDRs sitting on your desk, you're welcome to view my signal. So there's the analog. And now it's switching over to digital because it found the digital signal. And I'll just bring up GQRX as well so you can see it, see what it looks like. Try my luck here, see if I can run GQRX, a transmitter, and stream my video all at once. So there's a couple of commercial FM broadcasters. And what movie? Oh, the music? Actually, I just borrowed, I think it's a ringtone from Ubuntu Touch. I just looked around my user folder to find OGs that happened to be there because I knew I could freely distribute them if they were from an Ubuntu package. So there you go.
Any other questions from the audience? All right, one more round of applause. This is excellent work. Thank you very much, Clayton. Oh, back to the old static.
Turn that off.
All right, so we'll move into our next speaker then. We have Phil Kahn here. So we'll just take a moment to set up, and then we'll.
Yep, right there.
My demo stops running as soon as I do this, right? Okay, should be on. All right. I'm Phil Kahn. I gave a talk this morning. Some of you may have attended about at the GRCCon about ham radio and its use in education and so forth. This is kind of a derivative of that project. I did not prepare for this at all. I mean, this is kind of a last-minute thing. I don't expect this demo to work. If it does, I'll be amazed. But one of the things I've been working on off and on for a while now is very low-end SDRs. Using very inexpensive dongles. Everybody's familiar with RTO SDR, but there's some other cheap ones also. But I'm targeting hams who are interested in the internals of communication as opposed to just talking on the radio. And given my own past experience in writing internet code that people found useful as a teaching tool, I'm trying to do the same thing with my code here. Now, I will say I'm not using GNU radio for this. I'm writing in C. I'm writing from scratch. I mean, basically everything except things like codecs and FFT libraries. I'm still not decided if this is the right thing to do or not, but I'm also trying to keep it very small and very minimal. I'm definitely a member of the engineering school that says that you're not done when there's nothing left to add, you're done when there's nothing left to take out. And I see an awful lot that I'd like to take out of certain projects. I mean, for example, okay, I'm using ncurses as my interface, okay? It's 30 years old, 35 years old, but it still works fine. You know where it really shines is in remote access. I want to be able to put this up on the top of a mountaintop and access the thing remotely. And I've watched too many people running fancy GUIs through VNC so they can adjust the volume control. Okay, meanwhile, you got 5 megabits per second of video streaming over this link, which may not be able to support 5 megabits per second. So I'm trying to keep things really, really simple because I remember a time when it was actually possible for me to understand everything that was going on my computer. Now, I know those days are long gone, but I'm trying to capture at least some of that where you can actually take the whole project and put it in your head. So I'm trying to get rid of as many unnecessary layers of abstraction as possible to make something that can actually be taken apart as well as something that can be compiled and run. So the hardware that I'm using is one that I don't think a lot of you are familiar with. It comes out of the UK. It's called an AMSAT UK FunCube dongle. The FunCube project is an AMSAT United Kingdom CubeSat project, And along with that project, which is satellite, which has been in orbit now for some time, one of the members did a very simple SDR based on the Merrick's tuner chip that's, I think, used now a lot of other SDRs. But instead of using a wideband codec, he just used a high-quality audio codec. So it samples at only 192 kilohertz. But you know, that's actually a lot for what we want to do, especially for running on HF or the amateur VHF and UHF bands with narrowband modulation, which are low-speed digital signals, which most hams are doing. And it also has 16-bit width, which is wider than most other codecs I know. So this thing is actually quite good on HF. I mean, you need dynamic range on HF, and it's actually surprisingly good for that. But it was originally designed for satellite operations, so I thought I'd try to find a satellite application for it. This unwieldy-looking spider-like device in my hand here is it's a fairly common, very popular antenna for portable satellite operation. Most amateur satellites operate on VHF and UHF, so very often are in crossband because, you know, full duplex operation on the same band is usually impractical. So very often they'll listen on the 70 centimeter band, 435 megahertz, transmit on the 2 meter band at 145 megahertz. So this antenna combines two Yagis in one mast. It's great for like field demonstrations. I mean, it's not really for serious operation. At home, you have antennas with rotors and much bigger, provide much better performance. But this is great for demonstrations in schools. You know, just going out in the park and showing people stuff like that. So I had this idea a while ago. I got this Raspberry Pi. I've been doing a lot of work with Raspberry Pis. I always find a use for them. And I got one of the Sense Hats. The Sense Hat is a little daughter board, sticks on top of Raspberry Pi, and this one has, it was originally developed for the ISS, and then they made a mass market version of it. It has an 8x8 LED array, has an IMU, it has a bunch of other environmental sensors, and I got it mainly to play with the IMU, and I'm trying to think, well, what can I do with this 8x8 array? It's too small to really show any pictures, and I suddenly had this idea. What if I tape this down to one of these antennas and run a tracking program on it to tell me where to point the antenna? Okay, so that's the step. It's not. This is just a prop. I mean, it's real hardware, but the software is not running yet because I'm still working on it. But actually, this tracking software is running. The SDR software is running. It's a matter of integration now. So the idea is you can point this, you know, wherever it tells you to point it. It's also running the SDR program. It's got a GPS on it for timing and a frequency reference and location, of course, because you need to know that where to when you're tracking a satellite. And it will also Doppler tune the radio. So the tracking program sends messages over to the SDR, and there's a separate module in there that does Doppler tracking. So to tell you the truth, I don't actually expect this to work very well because here I am taking a computer and putting it right in the middle of an antenna. Okay, I don't expect that to work, but it was a neat idea anyway, and it's worth a try. Okay, so anyway, that's my idea. I know this is kind of half-baked, but I'm still working on it. Ballant kind of twisted my arm and like, you know, told me to talk about this, so here it is. Not much more to really say about it. So. And if you actually want to see my SDR stuff coming, I think it's got stage fright right now. Come back and see me later. It's working. I'm tunneling into home and running it from home. Were there any questions, or I didn't hear any questions? Okay. Well, I did, and it stopped working, so I don't want to waste their time. If anyone wants to see the demo, I can see it later.
We can, people, I'm sure will be willing to wait, and we can take questions in the meantime, maybe? You want to try that?
I'm not sure I can do both at the same time. But
okay. Well, we can give Phil a minute or two to set up his demo, right? Sure.
Yeah. I didn't plan to do this, so, you know. I'm also streaming over my phone, which is getting quite warm, so that may be the problem here. Yeah. So unfortunately, I bought more data minutes last month. So,
so just in preparation for our next event, Nate, do you want to go next?
somebody going next? Or?
Okay. Well, do you think?
I think my connection dropped. So yeah, I don't want to waste your time. They can see it later. So.
Okay. Maybe we'll try again after. 2-minute break while Nate sets off, and then please feel free to grab it on the slides. What?
Just started it. Good to go. Test 1, 2.
All right, Nate's all set up and ready to go. So let's get back to it.
Oh yeah, sure.
You ready?
Yeah. Oh, jeez.
Okay, our next speaker is Nate Temple,
Let's see.
and he's going to talk about getting on the X-band, a continuation of his previous Cyberspectrum talk.
Yep.
Round of applause for Nate. Take it away.
So I did a talk previously about my amateur attempts at building a satellite tracking system, the last Cyberspectrum. That system operated on a L-band and targeted L-band satellites. I've since moved on to an X-band setup, and I bumped the video. There we go. Since moved on to X-band, I left down my last talk with this pile of parts that I'd combined, put together to do so. So we have a waveguide LNA that was donated to me, and then a slew of other mini circuit parts and your typical RF Legos. So
Very expensive RF Legos.
yeah, very expensive RF Legos. So I bought some aluminum slugs to turn down to create a feed. So did that on my lathe. And here's a quick little video of working on the creating. It's called the Super VE4MA feed. So it's kind of like one of those pictures. I don't have that many in between. It's like how to draw an owl, like step one with a circle, and then it's boom, it's done. So this is just the inlet feed. A few pictures here. So then I basically made some flat spots with my CNC machine, drilled and tapped it, some set screws. Moving on to the transition piece, I got some 28 millimeter copper tubing from the UK because it matches the desired waveguide size. And so I CNC'd a piece of Delrin to match the ID of WR112 waveguide material. So I had a form to hammer it on. And it came up nice and square. The picture here on the right is, so I soldered then that transition, and there's also a depolarizer, which is kind of hard to see. And also starting here on the back side of the, this is the LO feed. I run a 4 gigahertz signal up from, it's a GPSDO locked B210 up to the feed where it's then ran through an amplifier, a frequency doubler, and another amplifier. You need to have plus 10 dBm to the mixer. And then here it is all up on the bench being tested. And miscellaneous parts, some of the more key parts that I use from mini circuits. So this is all going on to a repurposed 10-foot C-band satellite dish. So I took the choke ring from that and put it on my lathe and basically cut it all down so I could just reuse it as a mounting plate. So here it is with the start of the sled, I call it, which will hold everything. And you can see here the depolarizer, USA Satcom, or I'm sorry, UHF Satcom on Twitter made this for me. The depolarizer, that is. So here it is coming along with hard lines, getting wiring and everything, power distribution mounted. Side shot here, this is where the 4 gig LO is attached. And adding additional support for the whole frame. So this is my little totally cobbled together random pieces that I had for a power distribution board. And I had designed some PCBs to take your regular like 7805s or 7815s with capacitors to smooth out. So these are just where I attach the batteries and have a cool, you know, couple switches. Another shot of it. So RTL-SDR for scale on there. So I got this dish for like $50 delivered to my house. I drove past my neighbor's house all the time, and he had this monster dish sitting above his roof. And one Saturday, his garage door was open. I flipped around and went back. I said, "Hey, you want to get rid of your dish?" He said, "I'm happy you stopped because, you know, we're painting our house and we're taking it down, throwing it away." 10-foot dish, it's really not that big, like when you have like the 4 pieces of it, but once you get it all put together, it's like, you know, quite a bit to handle. So I modified my azimuth elevation mount to have this additional offset to it. The offset dish that I had has like a 24-degree offset to it, so it worked with just having it on there without any additional angle to it. But since this is not an offset, I had to have that extra angle in order to get lower to the ground. So here's the whole thing going together, and the dish got up on the mount. Another shot of it. So here's a little video of it moving. So we're looking at a geo satellite, DSCS-3, and as I move off of it, the signal goes away. Some more. So this is 50 megahertz we're looking at wide. So these are some rather wide channels. And another one. These are all either 8 gigahertz plus or minus the IF. I didn't have any front end filters on it. Another really interesting one is this hopping. This is 50 megahertz wide. It's a constantly hopping. So my big push for this whole project was I wanted to capture Cassini, which is plummeting into Saturn basically tonight or tomorrow. And there's a UHF Satcom on Twitter. He does a lot of amateur DSN work, and this is really what inspired me to try to get Cassini before it crashed into Saturn. If you look up his Twitter, he does all sorts of really awesome stuff. But unfortunately, I ran out of time coming to GRCon, and I wasn't able to do it. But there's some, there's Terra, Aqua, SNPP, the JPSS projects that are all coming up. They all have X-band downlinks and have various visual imagers. So those are the next on my list, and those are all rather strong signals. That's pretty much it. Got to give a special thanks to Patch Von Braun for helping me out, donating the waveguide LNA to me. UHF Satcom and USA Satcom, both extremely helpful. And special thanks to Cyberspectrum for having me talk and always putting on cool, talks and discussion.
Nice work, Nate. Any questions for Nate?
So for the microwave, and for the guys that don't know anything about microwaves, what's a depolarizer?
So it's a circular polarized signal that's coming in, and that's my understanding is that's like a WR90 size waveguide, and it will basically depolarize that from being a circular to a linear signal. Microwave black magic.
Did you have any intermediate test points? Because the way you presented it sounds like you just assembled a million things and then pointed it at a satellite and it just worked. But I'm assuming that's not what you did, right? So, while you were working on the waveguides and did you have ways of knowing that it's actually doing what you think it's doing?
So I did. I have I bought a Signal Hound 13 gigahertz analyzer, and I did test basically each stage, right off the LNA, with my random test signals. And the down conversion and all the steps through that. There's also not pictured as various IF filters as well, so it's not, there's no extra signals getting in there. It's all hardline, basically.
Have you calculated a G over T figure of merit for it yet?
What's that?
Have you measured a G over T figure of merit for the system yet?
I haven't. No.
Have you any idea what the noise figure for that amplifier for
So
is?
the first stage, it's like a 60K noise figure and 55 dB gain. It's a rather expensive LNA.
I wanted to ask Son, what started first as far as your hobbies and skills? Were you doing machining before you did radio and electronics, or were you doing electronics before? How did that work?
Grew up doing mechanical stuff, and so I got this lathe for this project, and that's my first major lathe project. I had bought a little one for the dish build I did, but I'd get a bigger one for this feed. Yeah, and there's more coming up, so.
More lathes and more projects.
More projects. Yeah.
Yeah. On the feed that you machined, how thick are the walls on the edges, and what percentage of the aluminum that you started with is left in that?
I think that was a 3-inch diameter slug, and the final OD was 73 millimeters, I think. So there was a lot of material removal. In the walls, they're pretty thin, like 1.5 millimeters maybe. There's several papers on that Super VE4 MA feed, and depending on your FD ratio, and there's multiple, and what type, if it's an offset or a center fed dish, you can have different efficiencies with offsetting where the choke ring is at, and basically every little setting. I just kind of went with what was right in the middle for a 0.4 FD dish and machined it up. Any other questions at all? Where'd the ball go? Okay.
What pointing accuracy makes a significant difference on X-band? 1 degree, less?
Yeah, it depends on your beam width of your dish, really. I mean, that's the main thing, as my understanding. It is, I mean, it has to be right on. I mean, you can pretty much within a degree, and you won't see it. Like, as soon as in the video, like as soon as it moves off there, it's the FFT is going really slow. And also I did test it like by putting something in front of the waveguide input as well, and it goes away.
I was just curious, what frequency band coverage, how far up in the X band can you go, and how low do you think this setup will go? Just curious.
So this, I designed the feed and the waveguide 28 millimeter pipe. That's all targeted around 8.4 gigahertz. The LNA that I have, it has 800 megahertz bandwidth with less than 1 dB ripple over that 800. I suspect it should probably work from 7.5 to higher 8.6 or 8.8 gigahertz. There's not too much interesting that far up. Like around 8.4, you're gonna find all the amateur or all the DSN objects, stereo A. Then there's also like around 7.8 gigahertz. There's some more interesting stuff like the Terra Aqua. JPSS one's going to be at 7812, I think. I have another feed, or another waveguide LNA feed. That's a WR90, which I may use for that mid 7 gigahertz setup, and just build a whole nother feed, and reuse a mixer in the LO generation part. That was kind of one of the points of I wanted to have a reconfigurable down converter. You certainly could have just bought something off the shelf that was probably cheaper than putting it all together. And I wanted to be able to reconfigure it if the mixer, the amps, and everything I have go up to probably 12 gigahertz, if I remember right. So pretty much from 7 to 12 gigahertz, I can reconfigure the setup with a few minor changes, a few filter changes, and it should work throughout that band. And well, the mesh too. Depending on the mesh size of the dish, it kind of determines your highest frequency. But this is a 2 millimeter by 2.4 millimeter hole, so it covers, yeah, it goes up to 12 gigahertz.
All right, let's give Nate another round of applause. Thank you, Nate.
plenty more birds to chase once you
Yep.
get back home.
Yep.
All right. Have you still got the mic on? So what we're going to do is Phil has actually set up his link again, so we're going to do take 2 on his text-based interface, which is
No promises.
Good to stream over his cellular connection at the moment.
This is all held together with chicken wire and chewing gum. A bunch of SSH connections that keep dropping. So, what this is actually running in my house. I mean, doing SDR demos in the field at HF is kind of difficult if you don't have any antennas. But let's see if this works. First of all, so you can go hear something here, and then.
Is it dying?
Okay, I think it should have switched over to the new screen.
Okay,
All right, now let's see if it's actually working.
Oh yeah, I saw something update.
There we go. All right, that's working. Some of you may recognize that sound. Do we have an audio connector or audio input? I know actually we're going to blast people with WWV, but okay. Okay, what this is, let me mute this.
1 2 1 2.
Yeah, that's WWV on 10 megahertz that's heard from my house. Okay, so what's actually happening here, and I won't inflict you on you any longer than I have to. Why isn't it showing up on the screen? I hate Apple. I mean, I just had to buy this new laptop because my other one basically was unrepairable. And of course, you have to get a dongle for everything now, including, HDMI. So what I'm actually doing here is I'm SSH'd into my machines at home. I have actually I have several Raspberry Pis that are each have a FunCube dongle on it connected to one of my antennas. They're all connected to my home network. They're all multicasting IQ streams over that network. The program you see running in the window in the upper right is running. It's running on a Linux, an x86, but it could easily be running on a Raspberry Pi. It's also my home network, and it's listening. It joins one of the multicast groups. I tell it which friend I want to listen to. It then demodulates it, and in this particular case, I am streaming the PCM output to a named pipe. The named pipe is then being encoded with Opus, so I can compress it over a network, and then I SSH in over to play it back. I mean, is that chicken wire and chewing gum or what? But I mean, I just hacked this together like last night. So
it is the finest chicken wire and chewing gum we've seen in a while.
Yeah, but like I said, I mean, I want to be able to operate this stuff easily remotely. I mean, I had plans to put this up on mountaintops. Mountaintops that get snowed in the winter, and you're not going to get up there for 4 or 5 months. And the links up there are, the communication links are very thin and unreliable, and I'm not going to be doing VNC over those links. I can't stand VNC over an Ethernet. I know anybody stands it over a real internet connection. So good old curses, is not a bad way to go. It's a very simple, very functional interface. You can move around and change parameters if it hasn't hung up again on me. You can move around and change parameters. If you happen to have if you happen to be running it locally in a Raspberry Pi, you can plug in one of those little Griffin Technology mate knobs, and move around and tune numbers. And then the other windows simply show all the numbers. I mean, everything that your radio geek or somebody who's learning about radio might want to see for the first time. So that's pretty much it. Yeah, like I said, one of the things I wanted to really do here is explore the use of multicast in SDR implementations. I've been asking around, and there's, a few people have experimented, but not a lot. Everybody seems to run everything in one box. And I think there's a lot to be said for making aggressive use of IP multicast, because you can easily have several boxes listening to the same stream. One box could be recording the IQ stream for posterity, for debugging later. Another one could be running a receiver like this. Another one could be running a spectral display. They can all be very modular, and because it's multicast, I mean, the sender doesn't care how many of these listeners there are. And then the output itself is also multicast, so you can also have as many syncs for that as you like. So really, it's more of an experiment in multicast than anything. I've noticed that there don't seem to be a whole lot of standards for metadata on multicast IQ data. If somebody knows of any, please let me know. I don't want to reinvent the wheel here and come up with something incompatible. But I'm sending it out because an IQ stream looks an awful lot like a stereo audio stream. I'm just sending it out in RTP as a stereo PCM stream, but I do have a special header in the beginning of each, after the RTP header, giving the sample rate, the RF frequency of the tuner, and gain flag settings. And it's basically all the information you need to understand what's going on. And when I play back a recording, those are also stuck out, and so that you can see you won't be able to tune beyond the the capture range of the front end, of course, when listening to a recording, but you can certainly tune around within that. So that's pretty much it. Again, I don't want to push this too hard, but I do have a broken pipe, of course, why not? I do have a third machine sitting on my network. Does not have a FunCube dongle on it, but it's running a program that's multicasting anyway. I do have a local simulation of that program that some of you might find amusing. Let's see if this works. Yeah, that's one night I just got into a hacky mode and I wrote an emulation of WWV. Why, I don't know. I mean, I was frustrated by HF propagation being so unreliable, and I was relying on it as a test signal, right? So actually, I emailed the guys at WWV. They love this thing. They had a good time with this. I also used it during the eclipse, believe it or not. We were in central Wyoming, and you would think in central Wyoming you would not have any trouble getting WWV, but I did. So I ended up just running this on my laptop, synchronized.
3 hours 47 minutes coordinated universal time.
And if there's a WWVH mode. So if you happen to know WWVH, you'll hear the differences. Higher pitch tick.
Round of applause. This is really cool, huh?
It's a hack, I could probably think of some pranks to pull with this and some hams, but I don't know.
Wait till you hear the long form message.
Oh, the long form message? I guess I could do that. I could actually force the time to do the message. How about that? All right, what the hell? If I can remember the arguments here. Let's see. Minute 59, second 45.
The font size on that window?
Oh, sure. Let me just see if that works. Oops. I don't remember my own program. Oh, I forgot S here.
At the tone, 4 hours 0 minutes.
That's the WWVH model.
Time.
Oh, I'm sorry. That was, I have to go a minute earlier if I want the WWVH announcement.
At the tone, 3 hours 59 minutes coordinated universal time.
And there's a pause for WWV announcement since they share frequencies.
National Institute of Standards and Technology time. This is not radio station WWVH, Hawaii, broadcasting on internationally allocated standard carrier frequencies of 2.5, 5, 10 and 15 megahertz, providing time of day, standard time interval, and other related information. Inquiries regarding these transmissions may not be directed to the National Institute of Standards and Technology, radio station WWVH, Post Office Box 417, Kekaha, Hawaii 96752, Aloha.
Okay, there are other problems with that recording that would clue people in that it's not the real one. I had a complaint that the Hawaiian words are mispronounced here, and I can't figure out how to fix them. The Aloha is correct, but the names of the town, I can't fix it. The male voice does them correctly, but that doesn't do me any good for a WWVH announcement. So, but anyway, I found this very useful during the eclipse. I just played it so I wouldn't have to look at a clock. I could know what time it was without having to take my eyeballs away from the telescope. And but as a concession to the non-ham family members around me, I put in an option to turn off the audio tones, just the ticks in the announcements, so that way they didn't lynch me. So.
You have that running around multicast on your home.
And I have to, yeah. If the band's closed, I just steer it over and I receive that stream, and it looks like it's on 10 megahertz, and perfect signal, no noise, and it just it's good for testing. So. Actually, I do have another a project in mind for this. I want to demonstrate, since I'm always trying to come up with ways of demonstrating ideas in new ways to students. I'm going to try to build a big correlator, massive correlator, basically using this as a local copy of the WWV signal, so you should be able to pull the thing way out from even the bands are closed. I should be able to get a correlation peak of some kind. And it would be a good demonstration of that concept. I don't have the voice, but I don't need it. I got the tones, I got the ticks. That should provide enough energy for me to correlate on.
And what about the subcoding?
Oh yeah, I don't know if you noticed, but the subcode is in there, and I think it's correct. I mean, the only hard part was figuring out all the daylight savings time rules. But I believe the subcode is correct. If somebody wants to actually go in there, I mean, I guess I could hide a a flag or something in there and have somebody try to find the bug. But that was the hard part, was doing the subcode. So I can also do leap seconds correctly. Okay, I can even do a negative leap second, which had never happened. Okay, and all the double ticks and everything all changed correctly. So anyway, thanks for your patience.
Thank you, Phil. Do you think you can? Oh, any questions for Phil?
But yeah, why did I do this? Are you nuts? You know, that kind of,
Yeah, anything like that, or something more technical? No? Are you going to make your own CHU as well?
I thought about that. Where can I get a copy of the spec of the exact error interface for CHU? I'll do it. Also, I need a French speech synthesizer. Yeah, the 300 bits per second. Yeah, okay. Okay, sure.
If we want to replicate this on our own home network, what can we do?
VPM. I could do any number of ones you want. You know? VPM is a Chinese station, which you'll often hear on the same frequencies.
So which mountain are you going to put your software up?
Mount Palomar. I'm a member of the Mount Palomar Amateur Radio Club. When you have a spot on the mountain, you know where. Those of you not from California, you might still know where Palomar is. It's the site of a famous radio telescope. And I'm a member of a radio club. A bunch of my friends in the back are also members of this club. And we do have a spot up there waiting for us once we get up there and get some communications in place. Actually, right now I only expect to receive. I mean, transmit requires a little more care that we don't interfere with anything, but reception is no problem.
And are you going to be releasing any of this code for others to use?
Sure. I mean, I don't like to keep things. I don't want people to look at it and laugh until I'm ready with it. So that's always the problem. When do you first release, right? That's always a problem. You don't want to release so early that everything's just going to change overnight, but you'd also like to get people to help and find bugs and contribute. I can be staring at a bug for 5 hours and somebody else will look at it and find it in 5 seconds. Thank you.
All right, and any other last questions before we move on to our next speaker? Josh, do you want to come down? All right, one more round of applause for Phil. Thank you very much. All right, so next up we've got Josh, and you're going to call me over Hangouts. Great. I'll set you up with mine.
First, otherwise I'll be
Now, I do realize that we got an extra delivery of pizza. Ken, was that you? I noticed that you brought it in. Did you actually order it as well? Where are you, Ken? Did you order it? Well, let's have another round of applause for Ken, too, for getting us more food. Thank you, Ken. Keeping us fed at Cyberspectrum.
I brought this time, and it works. Don't let me get my screen. Sure.
Well, you can pick up when you're ready.
I want to see mirroring. I think I'm mirrored. Okay, we'll make sure we're mirrored. All right, let's make sure it works now. What's up? No, I'm looking for the screen sharing. Is that's shared even though I switched tabs? And am I on the mic?
Yep, your levels are good.
My levels are good? I have to mute myself. This is the main audio. Oh, hey everyone.
Hi, Josh.
And we're full screen? No, we're not full screen.
Hide the little sharing thing in the bottom. We will hang up sharing.
Hide.
Okay, ready?
I still gotta need my audio.
All right, round of applause for Josh. Take it away.
All right. Yeah. Well, I didn't quite expect to make this talk, but I'm here now, so I'm going to do my best. I last attended Cyberspectrum at DEF CON last year. Valen hosted it. And this is sort of an update from that, but I want to tie into GNU Radio a bit. So the plot there is we ended on a little LoRa demo, and I had a kind of a simulation on there, and you can kind of watch the chirps go and actually decode a message. But so basically what I wanted to talk about is I got to talk a bit about SOAP SDR to GRCon, and so I also maintain this data flow processing framework called Pothos. So I want to talk a bit about, I don't want to go about it in general, but just sort of talk about I think some of the things that are neat that I've done. You know, we don't have in GNU Radio, or would be neat to see in GNU Radio. I want to talk about how I pull in GNU Radio blocks, and how I tie into the schedule and bring the blocks in, because I think that's pretty cool, and I hope that's not too low level for everyone here. And kind of going through this process, just some things I was thinking, you know, we should put in GNU Radio, or we should change. That would make it better, not just for this particular use case, but for everyone doing kind of interesting things at the low level, at the schedule level, etc. So we go on. What is Pothos? So we have a boring scheduler, just like there's boring drivers, and that's not very exciting, but it does have a GUI, which I'm going to try to demonstrate next. So don't worry, it's not just this slide. But it does some neat things. We can reconfigure topologies while running, so we don't have to stop the whole flow graph. For those of you that like to do sort of a Simulink-like simulation with feedback loops, that is actually possible. Now, feedback loops don't tend to be the most processing efficient thing, but you can do them, which is really cool. It makes it a complete simulation environment. We came up with a mechanism to do control over the flow, and this is signals and slots, and if you're familiar with Qt, you've probably heard of this, but if not, a signal is something a block can emit that has some kind of message, and a slot is essentially a call on another block, but the important part is this is done over a queue, this is done over a flow, and what this means is, well, blocks connected over signal and slot have a well understood connection, and we can do things like put them on different servers, and we know how to just generically deal with their connections. And I'll go more into that later. Something else kind of neat, polymorphic streams. And sounds complex, polymorphic, but what it means is essentially you can connect two blocks, and in GNU Radio I think all the stream types have to match, and they're really rigid about that. But here basically buffers come in, they have a little decorator thing, it's a few bytes that say what their data type is, and a block can not care about it. It can say, no, I only work on floats. It can not care about it and kind of deal with it in a generic way, so we can make like a waveform plotter, and you can connect anything to it. So we don't have to make different waveform plotters for every data type. So they can decide, I can handle this data type, I can convert it, or another neat thing is buffer forwarding. So if you're a block and you don't need to do anything to that data, you can just kind of pass it through from an input to an output. So something we do with Pothos is we're very flexible about buffering. So buffers can come into a block, and you can do the old thing you do with GNU Radio. You can read everything in your input buffer, do some math on it, write everything to an output buffer, but you can also get creative. You could say, oh, I know this part of this buffer has some header, and this must be my payload, and you can go forward them out as a message. And some guy who's can consume a message and do the reverse, and we can do this passive thing where, like, let's say we're making here's a good example, a block that's throttling, right? He just needs to pace some streams, so he can come in and he's got a buffer, and he just needs to wait a little bit because he's delaying the stream by some time. It's the throttle or pacer block or whatever in GNU Radio. He just passes it on. He doesn't need any output buffer. He knows what he's doing. So we can do kind of creative things, and I'll show some of that. And finally, a remote distribution, and this is supported in the GUI, so that's my demo. Basically, we've come up with a way to sort of represent blocks as RPC objects, and so we can essentially manage blocks running on different servers at the same time in the same topology, and what will happen is under the hood it transparently puts essentially network stream blocks in and out whenever you cross through a process, which might be on a different computer, for say, and so we can do that automatically. Cool stuff about the GUI. We have sort of a complete GUI. We can connect blocks and draw them around, and it supports a lot of those features. But I said this is kind of an update, so some new things we can do is we can export everything you've designed in the GUI to a little JSON comp file, and you can basically run that. and have your whole topology described in just a text format. And we're working towards doing like dumping that and re-importing it into like a hierarchy and stuff. So that's going to fall into future work later. Saving widget state. So maybe this has come up at some point. You ever set up your scope perfectly, and you know your scope sync or whatever perfectly, and you zoomed in and you decided what labels you wanted, then you closed it and it was all reset. So we've come up with a generic way for widgets and plotters to actually save their state. And so we can save that all with the topology, basically. And that's your slider positions, your plotters, whatever. Generic way to expose that. What else is cool? Overlays. That sounds weird. So blocks can basically provide a dynamic little piece of JSON that will fit into the GUI, and that affects parameters. How does this make sense? So if you have an audio device, an audio source or sync block, what devices are available? We can actually dynamically populate a little drop down for the source and sync block, so you can pick from stuff. Same with SDRs, so we can populate a little drop down based on the SDRs, and once you've picked that, well, things like what antenna options are available, we dynamically populate the antenna option, so I'll show that too. And let's see, there's the URLs. And I wasn't going to go into the scheduler stuff, but I think that's kind of neat. I did a bunch of interesting things with the scheduler, and so if you want to read, go for that. So let's look at the GUI. And tell me if it looks weird on the screen. Okay, I should have a few things open. Does that look good?
Yep.
Oh, it's just dragging something. Okay. I want to know. Cool. So here's something quick. I had a little demo with just this is the frequency translating FIR filter from GNU Radio. You can see we've nabbed them in there. So he's got all his docs and his blocks. Little FIR designer. This guy, I want to mention him. Tony Kirk, GitHub audio filter. He made a bunch of FIR and IIR designer blocks, and he has a great library called Spoost that provides generation for widget taps and all kinds of things like window taps and filter taps and things like that. So that's what I'm using. And eventually, he's also got a good graphical designer I want to tie in as well. So anyway, I'm going to run this, just show a few things. So translating for a filter from GNU Radio, mix and matching a bunch of blocks from other toolkits I've done. So let's watch it run. We've got the tone frequency, so we can control that. And then we're also controlling the filter translation, so we're not moving the tone. And I want to show how those are kind of hooked up. And so we've got little widgets here. Numeric entry is one of them, right? And this is what I meant by signals and slots. So this guy over here, numeric entry, let's make a new connection here. Delete that. So I drag. I get this window. So value change is the signal that comes out of a numeric entry, and that's all he does is he's just a message with the data change. And I send him over to set frequency. You know, I've got a new connection. So that's signals and slots. And a little bit of code. And what that looks like under the hood is anything that's basically a setting on a block. Set taps. Different one. It's a different block. Set taps. Set taps. It's just a call. So anything that's basically a function call can be a slot on these blocks, which is really neat. And all we had to do is basically, that's the C code with its setting, and he's just registered. So you make a C++ block, you can throw in all these calls, they end up being slots later in the flow graph. So we can look at things like, let's see, for a filter. You know, he's got slots on him, things like that. Okay, and what's a signal look like? Well, here's a slider, for example. So emit. No, none of it's. I took their concept. It's not Qt signal handling. Essentially, it's all just we built in a framework for connecting stuff and sending. When I said polymorphic, you can also have messages over any single port. Essentially, they're just normal connections in this thing. And then one of the things we can do is basically use that message. And if that message happens to go to something that is a function call, it will call that. You could also handle it as a message within the work function, but I didn't want to go into too much detail there. But you know, some widget. This is a block that's actually got an internal Qt widget, unlike some of the others, which is something you could do, and basically handle value changed. That's actually, funny enough, a Qt slot. That's Qt stuff, connect. And then he goes on here and value changed. So it's a slot to a signal, but this emit signal thing, yeah, that's basically producing a message. In fact, it's equivalent. You could just make a block that never knew any of this stuff, and it's just put a message on this port, and then we can go between messages and signals and slots pretty transparently. What's something? So whatever, that's boring. Let's look at this. One of the cool things is you probably didn't realize is I put all these blocks on here, but they're not actually all running on the same process. Funny enough. So by default, everything goes in this little scratch process in case it crashes. I didn't want the GUI to crash. And the other thing is all the widgets, well, they're GUI stuff, so they have to go in this GUI process. One of the cool things we have here is the rendered graph view. And this is the connection you probably saw. And this is dot generated. So top level view. Here's a flattened view. That periodogram, right? He was actually 2 blocks, right, under the hood. So we just flattened the topology and rendered. This is interesting. I said they're not all in the same process. So we've actually injected a bunch of little network blocks in here, if you didn't notice, and they're all hiding there. So, and last year we got to do a little funny demo where Balanced Computer was basically running an audio sync, and I had the whole thing controlled from the GUI, and we were driving sounds through it. So let's do something neat. While we're running this, I can go move it to another processor. So let's see, we'll peek at HTOP. So what I created these little affinity zones, and they're just, they could be different processes. Right now I made one that was only a particular core. So I can go take the design and just say, let's see, move you core 3. I actually should call it 3. There's 3. And then we can see HTOP. Nothing exciting. Let's pull out this pacer block. The graph should still be running. And there we go. There's core 3. So he set the affinity while he's running. All right, let's do one more thing, and I should also be able to say, all you guys, go to the GUI, and then we can look at our rendered graph view again. Is he still in there? That from that GUI. Did I not do it? Huh. Well, close enough. Shit's a bit weird. I'll debug that later. That should work. Let's see. What else did I want to show? Back to slide. Oh, yes, the overlay, real quick with the SDR. So I have a little example here. Let's see. No, nothing's in there. Nothing exciting. And there he is. So LimeSD are populated in there after I plugged him in. And you can go over, see, channels, and then antenna options. Any day now. I put it on a slow loop. Come on. I'll tell you what. I'll come back to me. You know, I don't do live demos, but I just tried this before I came. There we go. Look at that. So we queried the antennas live and oh, yeah, you get a picture. Oh, you want a spectrum? There we go. We got some noise. Let's see. Oh, one more. I did say I want to show you widget state. Let's see if we can really mess something up. So here's the frequency. All right. Now save. No, I don't want to save that guy. All right. You remembered. All right. Yeah, this is all Qt based. So we basically have a generic framework to not just make blocks, but you can make any block that's basically Qt. And essentially, I don't want to confuse anyone, but here's the periodogram, and he has an associated widget. So when I've inserted the block, which has the connections you expect, you can say insert graph connections, and you get the widget. And you can, and those all the settings will remain. And we can do things. One more cool thing: create a new graph page called Untitled. Let's go move a few guys on there. Say move graph objects to Untitled. We get a little breaker, and they're still all connected. So if I obviously you want to coordinate which widgets are where. One idea in the future is that these multiple tabs should actually go on multiple monitors. But I'm a one monitor guy sometimes, so there's a lot of good issues in the GitHub tracker. So that's all well and good. That's basically the update on that. It looks pretty cool. There's definitely a lot of future work I have in mind. One thing is we're managing a lot of active objects in the screen there, and so if I have multiple tabs open with all the same SDR with different configurations, it doesn't work so hot, not surprisingly. And so I do have an open bug on that in the issue tracker too, because someone else noticed. But we need to do some more creative things, like basically not always have all the blocks instantiated when no one's looking at it or running it, so we need to have an option for that. And I want to do future things, like I tried to show there's some remote interaction there. But one thing that would be really neat is to be able to sort of disconnect all the GUI stuff and leave the crap running on a particular server and come back later and reconnect. So I want to have kind of a headless mode for this in the future. And that should be possible. Most of it's a lot of GUI work. The framework's all in place for that. So that's basically a little update. I just want to show you some cool things. Again, it's all early off the cuff, so sorry if that was a little boring. Since I wanted to talk about how I was pulling GNU Radio, and I thought I'd briefly say like what we do to bring blocks into this design and what that kind of looks like, and that'll follow up with GNU Radio. So essentially, when we make a block, I've come up with this block description format, and it looks kind of like Doxygen. And everything you need for the GUI element outside of actually, the C++ processing, including, non-GUI blocks, like this filter, is described in this little markup. And so we have basically a title, documentation. You can use HTML if you like, categories, keywords, all the parameters, and these just have to match up with the actual parameters used below. And essentially what we're able to do is just you transparently throw that in your code. You have multiple header files, CBP files, just put it in one of them. It scans that. It knows to look for this little tag here. And we've thrown it in what's effectively a JSON format. And although we don't usually want people to have to write the JSON format because this is actually more compact and straightforward and looks like comments, we actually use this same JSON format when we pull in other stuff. So this is we actually generate code for pulling in GNU Radio and for Liquid DSP, and so internally we generate JSON. So this is the block description markup, and I sort of document what that looks like and how we also can specify different widgets we want to use within the GUI, and so some screenshots of that. And at the end of the day, we turn it into JSON, which we build along with the blocks. It's all embedded in there. Actually, you can show it. Just quickly, I don't want to. It's embarrassing. I'm showing you JSON, but it's in there. Woo! All right. And so I don't know how you feel about writing GRC XML files or YAML files, for example, but actually I think this is kind of quite nice and maybe something that we could look in for GNU Radio for similar purposes. I mean, if you can just parse it into YAML at the end of the day is my point. All right, too many tabs. So let's talk a bit about, okay, some features in the works, going headless. Screw that. Okay, So let's talk. Let's go into GNU Radio bindings. How do we do it? So I showed you we had a translating filter in there, but actually what we're doing is scanning basically all of the header files with something called a CPP header parser. It's someone created a really cool project that basically can scan like a header file and give you kind of a structured thing in Python where you can just pull everything out. And we're also scanning GRC XML. I mentioned this in the conference. Oh my God. They're a bit complicated. So we have quite a mess of code to go through them. But essentially, we've scanned GRC XML files to get out exactly what you'd expect, all the parameters, all the things that are setters and getters that we care about. And we generate them. So I'm going to show this running, and it has colors, so it's kind of nice.
Josh, who is the original author of that complexity?
Yeah, so, well, you know, it wasn't fair. I just had to work with what I was given. I couldn't really change GNU Radio, so there's something to be said about making everything structured, because then you can do more automated stuff later, and you can write a tool like the GUI I just showed you, and he kind of deals with things in such a generic way. So we never really generate things from templates. We just sort of specified strictly everything's a signal or slot. Everything's either parameter or constructor. And once you're in that kind of world, you can work from there. But lessons were learned. Let's see, build. I just want GR Pothos. Okay. So, and this guy can actually scan out of tree projects, but they have to kind of be in the right place. So let's see. He's going to run through, and this is all the stuff he detected in GNU Radio at the moment. I'm going to make clean. Watch this. Make. He's going to start scanning, and he's got colors. So look at this. We go through and we're reading all the XML and header files, and we'll tell you we don't. So a few things we can't do, or GRC confused us, and there's some mismatches. I've genuinely caught bugs in GNU Radio from reading this, and told someone about it, by the way. So that's cool. What does that look like quickly? You deserve to see the generated code. So there's a ton of JSON files in there. No biggie, right? We look at them. Just like I said, we pull out all the docs we can, too, from the header files. And the CPP header parser I mentioned is really cool because he actually recognizes doxygen tags. We like them. Let's see.
Where can we find this library?
Is it on the parser I just made? Parser. CPP header parser. Google that word. I've got a copy of it checked in. It's a single Python file, so I don't know if anyone sort of put it. I guess it's on GitHub, but I don't know if it has a homepage. It's one of those things where you want it to make it portable, so you just cram it all in one file. That's portable, right? All right. Real quick, I'll show the. I love to show you generated code. Okay. Let's see, ls_star.cpp. We're actually making, I call them CC files because GNU Radio uses .cc. That's how complete it is. So let's look what's in blocks. Every header I could find. All right. Basically, it's a factory to make a particular block and all the calls we need on it. And like normally you wouldn't write the code exactly like this if you're making a new Pothos block, but this basically works. Don't worry, it's generated code. But we've given ourselves a way to get a string name for every single function and that function. And from that, we know all the parameters on it and everything like that. And so we are just pulling in blocks. The other neat thing we do is we make our own sort of meta factories. So maybe you saw const multiply SS, FF, and all those things. And you actually, it's the scroll down sound. At the end of the day, we also like create little meta factories for this. So instead of like enums, we have a little type or something, and which one, and we dispatch it. So we can just have one block on the screen, just like you do with GRC actually. And this is actually the JSON. I escaped it, so I wouldn't have to figure out how to escape quotes. I escaped every single character. You weren't meant to read it, but.
What's your longest column with the?
Woo! If you can read that, tell me what block it is. All right. Okay, so that's how we generate. Oh my God, too many tabs. Who said tremendous success? Thank you. Should I parse the elf file? I don't know how to parse elf. CPP elf parser? .py. It works. It looks at the headers, which we expect Oxygen to be able to, and the compiler, and the humans, so it's not so bad. Let's see. Let's see, one more thing. Build, generate, plug in GR. I do want to show how it plugs into GR, and this will follow the next slide. So, okay, I showed you how we made like JSON and wrappers for all these things, but how do we actually call into these blocks? Because there's no API in GNU Radio to just make a block and feed it some buffers and run it for a bit and see what happens. So I did the lowest level thing I could. There's no fork to GNU Radio. We got right in there and and found where the buffers were hidden and found where the tags were hidden. And just real quick, what did we do? Let's see. Come on. All right. So I have GR Pothos block and not much in here, by the way. Pothos block.cpp. Where's my work function? So this block is doing all the magic by the way we interact with GNU Radio. So basically, we come in, my scheduler saying to work. So what does it have to do? Okay, did I get any messages? Let's pop them in. Let's just push them in right into into the block. Okay. Some message blocks in GNU Radio seem to do function calls that could produce new messages. So we had to basically say, did you give me any messages afterwards, and push those back out. And then we made sure, and then blocks seem to work like after that, as long as there's some inputs we can run. So we went ahead and checked a few buffer conditions, checked the input, and here we go, here's the magic. We went right ahead and got all the way into the debuffers, basically say, here's the pointer, here's the amount of elements I have, okay? Labels and tags, basically. Do we have any tags? Just we push them right into the block. The block has a space to store them, so we feed them over. Same thing with the outputs. All of our output resources, here you go. And then we, whatever size was available. And then here's the magic. We call the existing block executor and run one iteration. It's a weird looking file. You can go in it. It's got all kinds of corner cases, and we just run the default GNU Radio. It works. You saw it working. And then what do we do? Okay, well, some number was written that said how many things were produced and consumed, and then we use that exact same number to basically tell the schedule this is what was used. And then we go ahead and say, are there any tags? Okay, we're going to go push them on as well. And same thing, any messages. And that's all there is to it. One problem, all this GR buffer and GR detail stuff, it's all marked protected. So what did we do about that? This, I became a friend class. So I went ahead, I read buffer.h and basic-block.h all into a new file, and I replaced this semicolon kind of guy with friend class my block. Oh yeah, I should show you. What is it doing up the top? So I didn't bother including those headers. I had my own. Include first for public access to members. Real funny detail here. If you think you can just pound define away public and private, or like you can say pound define private to public and pound define protected to public, that works under some compilers. It'll actually create a different ABI under other compilers, and you'll crash. I found that out the hard way. So it might be the case. Yeah, it's a symbol export thing. Oh, that's the magic. So, it's the end of the live show, and I just wanted to talk a little bit about some ideas for GNU Radio. So, I hope I convinced you. You can definitely take a block and interact with it outside of the scheduler, and I think that's useful. But how about a formal API for that? And I wanted to sort of state my case. So basically, all we really need to do is we want to pick our own arbitrary buffers, pass them in, possibly tags, possibly you don't care. It depends on what you're doing. Call that executor, that crazy thing with all the edge cases. And then at the end of whenever it returns, we just wait on it. We say, okay, what did we get? And pop out anything. And so what can you do with it? Well, you could write, let's just say there's an API now to do this really simply, because you could wrap it all up, maybe include it with GNU Radio. Okay, now we can write test cases. So right now in GNU Radio, there's a lot of test cases where you have a block connected to a block, connected to another block, and we drive it in. But actually, in some cases, just you want to see something work, you could fill a buffer or the memory array and go call this function and then read the result. It would actually be simpler to do a lot of test cases. Further, I hope this is something that could engage people who are interested in future scheduler work. There's all kinds of computer science ideas out there. We have a ton of blocks that are meant to do actually like tasks. So we should be able to sort of connect them up and do weird things with thread and affinity and spin or scheduler things and see what happens just as an experiment. And we could all learn something from that and drag it back to the radio for that matter. There's that and yeah, I definitely mean to use these as kernels like NumPy and Volt. And maybe we could integrate better with hardware. So like if OpenCL wants to allocate you the buffer, well, you can feed this buffer right into the block now you were talking about. So there's definitely use there, or PCIe, or whoever's deciding the buffers for you, because right now GNU Radio picks the buffers. And it might be worth experimenting. We could fail. It could be a good thing. So that's always worth investigating. And finally, I could clean up GR Pothos, which obviously doing a few unsavory things there under the hood, but we're friends. I made you my friend. I just wanted to lay out one more thing we could do is you saw all that generated code and the CPP header parser and all that. Basically, I was thinking we could also register basically block classes and like how we get to like register their functions under some GNU Radio factory and register all the calls on it. And yeah, it looks like a mess, but you basically, if you built it in with the GNU Radio build system, every single block could be registered, just like we did there. And this is kind of neat because you can create a sort of really generic API to get at blocks. And so with just a set of parameters and the name of a particular factory, you could go make a block. And I wanted to make some sense of this. So we basically do this with Swig already. We scan everything. We turn into Python modules. But we could do this relatively quickly. We could do it on every block. It would be powerful because we could get this sort of generic API access to blocks, which means I can now describe everything essentially in like a conf file and build off of it. I could maybe tell a remote server, here's a small conf file, and he could build everything really generically, and he'd never have to see a header file. We could do away with Swig doing this. Because basically we can wrap this up in Python and we can give it an API that says here's the constructor. Do it once, maybe this in Python once, wrap it in Swig once. After that, assuming we had access to this factory thing, yeah, any single, but we'd have to do Python modules. Any single thing we could install, we can just sort of, if a particular module was installed, that we could instantiate in Python. We wouldn't have to ever look at header files. Your C project would never have to do anything like that. So there's some benefits to doing that, and it would save some other code generation I did. Oh, I wrote it here. Anyway. Yeah, that was the grutil execute topology. We describe it in YAML. Okay. That's about all I wanted to cover with that. I didn't lay that out really well, but that's the idea. And also wanted to mention we have something similar, Pothos Liquid DSP. We're also scanning the header files because I love doing this. And we're able to actually create all the same exact thing. And so Jay Gaddert's really good about this, and he wants to create a JSON file for me. So I'll have a high-level description of everything. So any kernel in a Liquid DSP we can potentially pull into a block, or at least save a lot of effort because it'll already be described at high level. Thanks. I'm a bit frazzled, but I hope that was somewhat interesting and enjoyable. There's my contact. Ask me any questions if I have any juice left.
Josh, the master of generalization and abstraction. Round of applause. Thanks, Josh. Any questions for Josh?
Yeah, so good news, bad news. It's like good news kind of reminded me what we were talking about like after last year's GRCon. Like the whole like Corgan is all for having like an abstract API that basically makes you like don't care about the C++ class underneath, but just like give me a multiplier block that does what I want. And also like the whole, okay, we should like totally have message acceptors or slots instead of setters.
Oh, yeah, that kind of abstraction. Yeah.
That's pretty much like, I'd agree that that's the direction that we want to go. But I certainly can't speak for like the project as a whole. So point is that, I mean, there's a lot of existing blocks. So really the conversion is the problem, and basically parsing the headers, like to make the conversion easier, might be the only chance we get at that. Because if we try to do that manually, we probably end up releasing.
We would do it automatically. You could do this, and I wanted to think more about it. I did this in Pothos. So just a generic sort of way to do it with classes. You can actually register the function in a string, and the fact that when you register a function, you actually get access to all of its types. And what happens is you're actually generating something that knows how to convert between PMTT and that type. And I don't want to argue. I can lay it out in more detail, but it's probably the wrong time.
I happen to have exactly such a message handler register for methods. So yeah.
Message handle for your thoughts. Perfect.
GCC has Clang probably better than Clang, but I know that GCC has a feature where you can print out the abstract syntax tree as or some intermediate stage as an XML, and then maybe that's an easier way to introspect code than either looking at the ELF codes or doing text parsing on header files. Have you thought of that, or is that?
Well, I am parsing it for the documentation, so I guess the registration stuff doesn't actually have to. It would have to know about the functions. No, I would want to do it in a cross-platform way, because there's probably something better than parsing header. At the same time, it is still pretty complete. You get a name of every function and the types, and you can definitely do it. I mean, I have done it. I just want to do it with GNU Radio too, and I could lay that out in more detail if need be. I just don't know about parsing it in something else. As long as it's cross-platform, it's like anything could be better potentially. I know we're friendly with Python, and the tools are there. So.
Still up the mic, but I don't have any questions.
You can.
Any other questions for Josh?
Anyway.
Or we could have two. One local, one for the remote. So thank you very much, Josh. One more round of applause.
Oh, thank you.
And now we're going to wrap up this evening's Cyberspectrum with two short demonstrations. The first demonstration is going to be from Alexander of Fairwaves, and they're going to demonstrate some cool new hardware. So we're just going to set up. Bear with us one moment.
I'll be out of your hair? Yeah, sorry.
And then don't forget to hang up, Josh. I think we're still sharing. Oh, didn't you close it? No. Put that on when you're ready. And then, do you want to call me? Mm-hmm. You are online.
Yeah.
I'm actually calling you.
Just 1 second. Yeah, sorry, just was, my browser was loading.
radio experience, I've got your picture. It's all good. You could probably pass that exam. So well worth spending the time. And thank you very much to everybody that's actually hosting the exam. I think Michelle made a point about it that in San Diego it's actually sponsored by an organization, so it's free. Who can read Morse code here, by the way? A couple of people. I was just saying.
The mic is off. Why don't you? I mean, obviously, Morse is not a requirement now for the exam, but just just for kicks, because it's an excellent mode of communication where you're dealing with an extremely narrow bandwidth. Who wants to give a try of this?
Who's the fastest? I don't have a prize for you, but. What? It's more of an eye test from here. Ear test. Are you ready, by the way?
Yeah.
All right. We'll come back to that later.
Go for that. Yeah.
It's fun. I didn't know, right? Do you want to click on hide down the bottom?
Oh yeah, sure. Is this thing working actually?
Should be a little light on it. Is there light on it?
All right, go ahead.
Okay. Oh, actually, I should have said we are not ready. Still, so really wanted to make a demonstration, but the software is not ready yet. So let me first start with introducing what Xtrix is. Maybe software will work by that time. Yes.
So if we read into that, your colleague is currently trying to make it work?
Yes.
No pressure.
Sorry, where is it? I should have made a. Where is it? Yeah, here. Yeah. So basically, Xtrix is a new software-defined radio, which we really plan to release soon, because we made a similar announcement last year. Said we will release it soon, and a year has passed, and we are still releasing it soon. But now soon is really soon.
Soon, like in the next 5 minutes?
Well, maybe, I don't know. We'll see. It's kind of unpredictable. So it may happen or may not happen. So because yeah, we spent the year fixing bugs and redesigning the board. So we just got the board from the fab, literally before the workshop. We were late for the workshop because we were waiting for the board, and it was delivered to us with a courier on an airplane, literally. The fab failed to send it to us with UPS, and they sent a person from San Francisco to here with a package. We really tried to make it. I mean, yeah, but as usual, new hardware requires some bring up time. So, the system sees the hardware, but something doesn't work yet. So I will just talk you through what is here, and I guess I can actually pass the hardware. So this is a mini PCI Express card, and unlike the only other mini PCI Express SDR on the market, it is going to be affordable. Affordable meaning it's in the same range as Blade RF and these guys. Sorry, I'm just what should they? Let's start with simple things, right? Who actually like sorry. Okay. So all the SDRs we've been normally using has USB on them, right? So that's kind of became the standard. More professional SDRs you can get from, for example, from Meetup Research. They have sometimes a gigabit Ethernet or 10 gigabit Ethernet or PCI Express. And the idea is that USB was usually the cheapest way until very recently to get SDRs, just because it's widespread and it's the cheap interface, right? All the RTLs are using it, and PCI Express was kind of out of reach. I actually wanted to make PCI Express or rather like mini PCI card for a long time, but it just wasn't possible. Sometimes because of the size, because RFICs, meaning like integrated RF chips, only became available just a few years ago, and before that you had to do pretty much like a discrete design for an SDR. Like remember USRF 1 with all this big daughter boards, right? Just couldn't fit into the form factor. So what happened over the past few years is that RFICs became available. So now you can have very miniature yet high performance SDRs in a small form factor. And at the same time, PCI Express is a kind of not the easiest bus to work with, and you can get a core for your FPGA from Xilinx or from Altera, for example, but you still need to write a Linux kernel driver, and you still debugging this becomes a real issue, because unlike many other, unlike USB, if you make a small mistake in your driver, your whole computer freezes up, right? So you have to reboot your whole computer, and you have to fix the bug, try again, freeze the computer, and things like this. So now and then you had to replug it, power down everything. It's very, very hard. So
how many times have you had to reboot your machine during the development of this?
Many. I don't know, but many. But the good news is that at least unplugging becomes easier because of Thunderbolt 3. So basically, Thunderbolt 3, which is a part of Intel version of USB 3.1, and Intel, all the new Intel chips are shipping with it. So my new laptop has Thunderbolt 3, Sergey's laptop has Thunderbolt 3. The idea is essentially it has a mode where it exposes PCI Express over a USB cable, so it becomes essentially a pluggable PCI Express device. So it literally PCI Express over a cable. So you plug it in, and from the OS perspective, there is no difference. It's the same PCI Express. Can do less PCI, and it will show up. So you can unplug it, plug it back, and that's it. So and it's really high performance. I don't remember exact numbers, but I think it has 8 PCI Express lanes or so. So it's a lot of throughput you can do. And I think that's kind of your high-performance SDRs are moving, like as Thunderbolt becomes more available on the market. It will be like more and more widespread, and I hope to see more of that. Unfortunately, Intel made Thunderbolt 3 hard to hard to develop, because you really have to like apply for a license to do it, and like not the cost is kind of not the real issue, but just the hurdle of doing this is really difficult. So we tried to get an official like Thunderbolt license to create our own converter, and Intel started asking us about, okay, please submit your business plan. Like, I mean, seriously? Please submit like all the documentation, everything, and then we will approve you. I mean, that's not really very helpful. So, but thankfully there are some converters from proper mini PCI or PCI Express into Thunderbolt 3 on the market. They're somewhat hard to find, but they are available, and they cost like $200–300, which is overkill. But again, for development purposes, I think that's okay. So I really hope that this will really help. And we spent quite a lot of time, probably like about a man-year, developing PCI Express FPGA core, which would be specifically designed for streaming, because there are other like easy to use FPGA cores for PCI Express, but they are mostly designed for like low-speed communication, for like I2C, SPI, and the control stuff. And when you try to put like good amount of data through them, they just don't keep up, and you can't reach more than 50% utilization of your bus. So we tried to achieve like 90 something. I don't remember exact numbers again. Like it's 92–95% utilization of the bus with our module, and the idea is we will try to make it open source and available. So hopefully it will be of a good use for other people trying to do the same. At the same time, I really think that mini PCI Express is a really interesting form factor, because it is embedded form factor, which means you can embed it not only in a PC but in another carrier board, right? So you can have a USB SDR of a relatively small size and just plug it in, right? So I mean, it's not much bigger than RTL at the same time. Yep.
Can I ask you about that? So that device you're holding there, that's a USB interface to plug into the host.
Right.
And there's an IC on there that bridges USB back to PCIe?
Yes, correct. So
and then what happens then on the host side? Is there a driver that?
Yes. So So this chip, if you can see my my cursor, this chip is essentially a chip which converts USB 3 into PCI Express, and we found only one chip on the market which can do this, like at least out of the box. But it exists. You can buy it on DigiKey. It's available. So what happens is that, on the host it's seen as a USB device, and then, well, you need to develop your libUSB like wrapper for this. So I don't have a picture. I don't have a picture with me right now, but essentially the way we designed our software is that there transport layer is abstracted. So a transport layer could be PCI Express or it could be USB, and it's just transport layer. Then it has the main logic, and then it has there also an abstraction for the ref layer. So right now we are using Lime chip. It could be something else, but the software is built in a modular way where all of this is abstracted and can be changed. So this also allows us to reuse this in different platforms, right? So the core stays the same. The driver level can change, so we can use it on Linux, we can use it on Windows, theoretically on other platforms, but I mean we ourselves don't plan to support other platforms, but Windows and Linux are totally possible here. So and again, you can also plug this into a full-size PCI Express, and there are converters where you can put 8 mini PCI Express into a single PCI Express card. There is a card called Squid. You can just Google Squid mini PCI Express. Costs something like $400 or something. And then you can just plug 8 of these cards and get a lot of antennas essentially out of your PC. So it's really easily scalable solution in this way. So I think it's really the way your SDRs are moving at right now. One other interesting thing is, where is it? Yeah, so we also I originally thought about implementing USB 3 directly on the FPGA, but turned out it's not possible for low-cost devices because of this very specific USB 3 mode. So essentially, FPGA, FPGAs that have MGT lines, which are high-speed serial lines, working up to 5 gigahertz. So, but the problem is on their low-cost Xilinx FPGAs, which we are using, these MGTs can't go at low speed. They only support high speed. And USB 3 has this very specific power-saving feature, which is called low-frequency periodic signaling. So if there is no data, the host can put you into a power-saving mode, and at power-saving mode, you need to send your clock at 10 to 50 megahertz versus gigahertz, and it's just not possible here. The high-end Xilinx devices support this, but high-end FPGAs are not what we're looking at. So unfortunately, that's not possible, at least right now. At the same time, yeah, this, by the way, USB 3380 is the chip which I was mentioning, which is converting from PCI Express into USB. So yeah, by the way, some testing we've done. Well, it adds 700 milliwatt of power consumption. So mini PCI Express cards are limited to 2.5 watts just by specification. So when we are pretty much at the same level, plus 700 milliwatts, so gives you 3.2 watts, which I think is not bad. And bandwidth is only 10-15% lower than original PCI Express. On the other hand, what we can do is we can implement USB 2 on FPGA. We have not done this yet, but we made the hardware to support this. So if you look carefully at the board, you may see that it has a micro USB connector on the side. This micro USB connector, again, right now is just a connector, not operational, but it's connected to FPGA so that when we write the FPGA code, you will be able to connect the board over USB 2 and either plug USB 2 directly, like as a micro USB, into the board, or Mini PCI Express is a funny connector because it says PCI Express, so you think, okay, Mini PCI Express must have the PCI Express, and the thing is, it has PCI Express, but it also has USB. And actually, Mini PCI Express modems, for example, like 4G modems, like LTE modem, 3G modems, they're actually not using PCI Express, they're only using USB. So all these Mini PCI Express modems you have in your laptops and everywhere, they are just the same chipsets as in USB dongles, just in a different form factor. And the point, this led to a situation where there are many devices like home routers which do not even route PCI Express into Mini PCI Express slots. So you may open your device, open your router, and see Mini PCI Express slot in there, and say, oh cool, like I can plug in some PCI Express in here. No, it's just like an embedded version of USB, pretty much. And because there are many such devices, specifically low power devices, we thought it would be really interesting for low speed applications to have a native USB 2 support, which is also much more efficient than even PCI Express, and not to speak about like USB 3 or like something even more advanced. So you can have, a very power efficient, low speed, very cost efficient version of the hardware without any hardware modifications. It's purely firmware change. And I mean, if you want something like really like fancy and advanced, you can implement some other protocols over the same MGT lines. That's mostly it. Like we also took a lot of care to make sure that the boards can be time synchronized, and as you may see on the board, they have a GPS built onto them, and plus, so each board has GPS DO built into, and at the same time, they have one PPS and reference clock in and clock out. So you can use one of the boards as a reference clock, and other boards will be the slave clocks, so as slave boards taking clock, and they will be absolutely synchronized in terms of sampling rate. So unfortunately, the PLL is not synchronized, but this can be done in software. And then, I mean, you can also use this just as a very fancy GPS clock source, because it's a PCI Express, and we connect the 1 PPS signal coming from GPS into the driver and expose this as KPPS in Linux kernel, and KPPS is a special Linux kernel subsystem for time synchronization. So you can pretty much turn your PC into a very high performance clock source on the network. So I think it's also pretty cool. Again, unfortunately, demo is still waiting.
Next year.
Next year. Yeah. Next year, definitely. That's it. If you have any questions.
Okay, round of applause for Alex. I think anybody that's involved in hardware design and creation knows that it can be fraught with peril and dangerous. So we definitely sympathize with you on this one. Look forward to seeing it working in the future.
Thanks.
Any questions for Alex? No questions? All right. Well, thank you for sharing that, and we look forward to future developments. So we'll end this evening there. Thank you all very much for coming out and joining us. Thank you to Qualcomm for hosting us. It's been quite a week with GRCon, and so we appreciate everyone spending their time and effort on the drive out here. Yeah, and thank you again to originally actually Mike Osman here gave us the hookup, and then Michelle closed the loop with her Qualcomm contact, and we managed to get this beautiful venue here. I think it's all worked out quite nicely, and as we say, stay tuned for future meetups. I know they haven't been terribly regular lately, but we all get a bit busy. But we're working on that. I'm leaning over to Neil's whispering things in my ear to say. So let's have a final round of applause for our speakers this evening, and thank you again. See you next time.